All right, am I on? Okay, good morning. Good to see you all up after the banquet. Yesterday, Jonathan sort of led us through some of the programmatic aspects of astrobiology and space missions. And this morning, I want to bring us back to the science and talk about some of the issues. In fact, we've been talking about them all week, so some of this will not be new. But I thought a fun way to do it is to go through some of the arguments that are raised in this book, Rare Earth, and also in books by Jim Lovelock on the Gaia hypothesis. So the format of my talk this morning is I'll go through a list of arguments that are made in Gaia and Rare Earth, and I'll talk about most of them real briefly, but then there's three of them that I'll spend a little bit more time on, one of which is the question of nitrogen, N2 in planetary atmospheres, which we've talked just a little bit about, but not very much. And then the frequency of large impacts and the effect of giant planets on large impact events, which of course can influence biological evolution. And then finally, the question of chaotic obliquity fluctuations and the influence of the moon on stabilizing the Earth's climate, because that's one of the sort of central points that's made in the Rare Earth book. Let me just sort of remind you about these books. There's a whole series of books on Gaia by Jim Lovelock, who wrote his first book on Gaia back in 1979, A New Look at Life on Earth. And then arguably the best of the Gaia books, I think, I haven't read all of them, but this 1988 one, Ages of Gaia, is really well written and has, by that time he'd sort of developed the meat of the Gaia hypothesis. So that would actually be a good one to read if you're interested in this. And I'm going to classify Gaia sort of with Rare Earth because the claim of the Gaia hypothesis is that life itself is what keeps the Earth, the climate stable and the environment habitable. And so if you didn't have life, the Earth would not be habitable, which of course then whether or not there are other habitable planets out there in the galaxy depends on whether they originate life or not. And if none of them have life, then none of them would be habitable if the Gaia hypothesis was strictly correct. So I'll spend more time with the Rare Earth argument. Peter Ward and Don Brownlee are the co-authors of Rare Earth. Peter Ward is a paleontologist. They're actually both colleagues of John Barris at University of Washington. Peter Ward is a paleontologist there, and Don Brownlee is an astronomer. Peter writes a lot of books. He writes about a book a year, I think. And this is probably not even his most recent book. This is the most recent book that I'm familiar with.
He's had 5 since then.
5? So this is a 2009 book. It's called The Medea Hypothesis, and I've just put that up there. The Medea Hypothesis is the antithesis of the Gaia Hypothesis. Peter in this book argues that life destabilizes the Earth's environment. And so Peter never did like the Gaia hypothesis, and so this was his attempt to respond to it. I don't actually recommend that book. I don't think it's Peter's best book. I think his best book is Rare Earth with Don Brownlee. And I'm going to, as I'll say this morning, there's a lot of things in Rare Earth that I disagree with. But on the other hand, it's a really fun read, and it raises many of the issues that we've talked about this week and some that we haven't talked about. So it's really a good way of sort of focusing your mind on the questions that are interesting for astrobiology and for the existence of life elsewhere. And the thesis of Rare Earth is not that life is rare in the universe, it's that complex life is rare in the universe. And by that I mean, Peter means animal life, metazoans. And of course that includes intelligent life, so the Rare Earth would imply that intelligent life is rare. Just an anecdote on that, Peter gave a talk at Penn State where I work back around a year or two before this book came out. And in his talk, he argued that life was rare in the universe. And I remember I went out to dinner with Peter. There were a whole group of people that went out to dinner afterwards, and I sat next to Peter, and I bent his ear for about an hour or so, and arguing that the habitable zone was reasonably wide and that there were reasons that life could exist elsewhere. And then I didn't have any communication with him, and when the book came out, the thesis had changed. It was complex life was rare rather than life itself. And I think that, it's actually, that's a much better theme for a book, because, there are many arguments you can bring to bear as to what, how you get from simple life to complex life, and some of those steps may be difficult. And so that's the part that I think is the most interesting for discussion. I'll just mention one other book because it just came out. This is a book by Tim Lenton and Andy Watson called Revolutions That Made the Earth. And they're also interested in this question of whether complex life evolves on a planet. Both Lenton and Watson are proteges of Jim Lovelock, so there's a lot of Gaia in there, although they don't toe the line necessarily. They're not as Gaian as their mentor, Jim Lovelock, was. But they also talk about, they're not really biologists, but they talk a lot about biology in there. And they bring up a bunch of issues that we should think about. They're rare earthers, they say so in there. They think that complex life is rare, and they think the reason they think that is that there are a number of steps that are individually difficult, and then you multiply the probabilities by each other, and they say that would be difficult to do. This is not a comprehensive list. This is the ones that I could remember. The origin of life, the origin of the genetic code, the development of oxygenic photosynthesis, the origin of eukaryotes, the origin of sexuality, and I see John already shaking his head here, so some of these steps may or may not be difficult.
Are these in temporal order, because the origin of the genetic code postdating the origin of life and the origin of sexuality postdating eukaryotes, or is it just a...
Well, actually, I read through it quickly, and that's what I could remember when I made up this slide. So that's not necessarily in order, and it's not a comprehensive list of what they discuss in their book. All right, so let's get to the Gaia and rare earth arguments. Most of these are actually from rare earth, and there's one from Gaia that I'll include in the list. We can start at the top here. Some of these issues we've already really dealt with during the week, and so I'll go through them pretty quickly this morning. One of the basic arguments in rare earth is that plate tectonics is rare. And I talked about that in my second lecture, that that argument was based on sort of just surveying the solar system and saying Earth is the only planet that has plate tectonics, therefore plate tectonics is rare. I think that's oversimplified, and I argued that plate tectonics probably requires liquid water, and so the reason that Venus doesn't have plate tectonics is because it lost its water. So if a planet is outside the habitable zone and loses its water, then that's also, that's the same criterion if that argument is correct. So we'll move on from that. And then, of course, on the other side, Mars doesn't have plate tectonics either, but we've talked about that. Mars is too small, so it cools off very quickly. So the moral of that is a planet needs to be big enough in order to, you have to have a planet that's bigger than Mars in order to stay habitable for a long time period. The second one is on magnetic fields, and I think I talked about this the other day also. The argument in there's really two arguments that they make. First of all, they say that magnetic fields may be rare, and I don't think that's necessarily true. If you have planets that are not tidally locked, like the Earth, as long as they're spinning reasonably rapidly, you can get a magnetic dynamo. There is some question for these tidally locked planets around M-stars, which are spinning more slowly, as to whether they'll have magnetic fields. And then the arguments that they talk about, the magnetic field helps to shield out cosmic rays that are coming in. But that argument, if you start looking at what cosmic rays actually do, most of them are absorbed by the atmosphere anyway. In fact, if you go up to high latitudes, the magnetic field lines are vertical, and the cosmic rays can get right in there, and you can still live at high latitudes. You don't get a high radiation dose. So you don't really need a magnetic field for direct radiation shielding. the more interesting argument is whether you need a magnetic field to prevent the loss of the atmosphere by interactions with the solar wind. And I think we talked about that earlier too, that Mars does seem to have lost a lot of atmosphere by solar wind sputtering, as it's called. But Venus, I gave that example, doesn't have an intrinsic magnetic field, and it's got a very thick atmosphere. And I think the thing that that allows Mars to lose its atmosphere is just its low gravity, so that the atmosphere is then more extended and it's easier to sweep it off. The thing that allows Venus to retain its atmosphere is the fact that it's a CO2 atmosphere, and so the upper atmosphere is cold and it's not that extended. And so the interaction with the solar wind is really rather limited for that reason. Moving along here, there's an argument in there about, they define a new kind of habitable zone that they call the animal habitable zone. And that's the region where the surface temperature on the planet is between 0 and 50 degrees C, which is the upper limit on life for metazoans. I think that's the same number that you showed us, John. So that's a good number.
Below 0 to 50.
All right, below 0 to 50. So they use 0 to 50 in the book. But then they compare that to the habitable zone, and here's the bad number. They say that the habitable zone is the region where liquid water can exist, and they quote that as 0 to 100 degrees C. But if you remember my talk on the runaway greenhouse on Venus, that's not right. There's nothing magic about 100 degrees C. And you can have liquid water at much higher temperatures than that. However, the actual critical limit in our habitable zone theory is much lower than that, because it's not the runaway greenhouse that defines the inner edge of the habitable zone. It's getting the stratosphere wet and losing that water to space. And if you look at the curves that I showed, you look back at lecture 8 or whatever it was, you'll see that the stratosphere begins to become wet when the surface temperature gets to about 60 degrees C in that model. So actually, if you look at the numbers, the animal habitable zone and the habitable zone, as I've defined it here, are nearly the same thing. So that's not really a special argument. All right, then there's an argument in there. This sort of relates to the galactic habitable zone idea. And an astronomer who was at University of Washington at the time was Guillermo Gonzalez. And I don't know if any of you know Gonzalez. He's an interesting character. But he had done some work on looking at the metallicity of nearby stars. And Gonzalez wrote a paper arguing that the sun is anomalously metal-rich compared to other stars in the local solar neighborhood. And this is this argument then, Peter Ward and Don Brownlee picked up on that as part of their argument in their book that we're living around an unusual star. But then if you go back and look at this, and I wasn't the one who did, but there are some other astronomers looked, Gonzalez included M stars in the local solar neighborhood. And of course, M stars on average are a lot older, and so they're more metal poor. If you just compare the sun with other nearby FGK stars, my understanding is the sun is pretty normal in terms of metallicity. So again, that's not really a very powerful argument that the Earth environment is rare. Then there are some biological arguments in rare Earth, and there's several of them that I don't remember, but these are two that really caught my eye, and which John I think would like. One is that eukaryotes evolved from magnetotactic bacteria. Magnetotactic bacteria are these big honking bacteria that have magnetite inside their cells, and so they can sense the direction of the magnetic field, and they use that to migrate up and down actually in the water column, because they take advantage of the tilt of the magnetic field lines, and it's pretty hard to tell up from down when you're a single-celled organism floating in the water. But if you know where the magnetic field is, you can migrate to higher or lower levels. That's, I think, why they do this. And this idea comes from Joe Kirschvink, actually, at Caltech. I've mentioned Joe's name because he was the person who first thought of the snowball Earth hypothesis. Joe is really very creative, you know, but Joe has lots of ideas. Just like Peter writes a book every week, Joe has a great idea every week. Well, he has an idea every week, and some like snowball Earth, I think, really are powerful ideas, but this particular one is not so great. Joe studies magnetotactic bacteria, and so I think that's why he likes this theory. This other one comes from Joe Kirschvink, and so this one has to do with the Cambrian explosion in the origin of complex life. Actually, in rare earth, they list 4 different possible triggers for the Cambrian explosion, and I've by now forgotten most of them. I know one of them is the rise of oxygen, which we've talked about as a possible trigger. But the 4th one that they list, and the one that they seize on in the book, is another Joe Kirschvink idea. They claim that the Cambrian explosion was triggered by an inertial interchange event. And inertial interchange, this is kind of cryptic. Sometimes the planet's crust can switch direction compared to the mantle. And you know, bodies like to rotate around their principal moment of inertia. So if you build up mass, suppose you've got the planet rotating like this and you get some kind of mass bulge that's not near the equator, then it's possible for the crust to readjust on a time scale of millions of years and just shift like that without shifting the Earth's rotation axis. We're pretty sure this happened on Mars, for example, because on Mars, I showed you a picture of Olympus Mons, which is part of the Tharsis bulge. There's this huge volcanic bump on Mars' surface, which is Tharsis, and Tharsis sits right on Mars' equator. Well, why is that? It didn't necessarily form on the equator. It formed at whatever latitude, and then that changed the moment of inertia of the planet so that there was an inertial interchange event, and that Tharsis migrated to the equator. In fact, there's been a paper, I've forgotten the authors, I think it's Jim Head's group, or Facet and Head, where they actually argue that you can explain the shorelines on Mars by doing that. Anyway, this comes from Joe Kirschvink because he does paleomagnetism, and there's evidence in the geologic record that such events may have occurred in the Earth's history. And Joe found evidence for one just prior to the Cambrian. So then they seize on that somehow triggers the Cambrian revolution. And I can't remember the logic of why that does, but you know, that's a weak rare earth argument. All right. So those ones you can dispose of pretty quickly, I think. But then there are some better arguments in there, and that's what I really will spend a little bit of time on. There's an argument. This one comes from the Gaia hypothesis, not from rare earth. The argument from Lovelock is that nitrogen may not be abundant in a planet's atmosphere if life is not present. And I've got some slides on that, so I'll come back to that. And then this one about large impacts. In rare earth, the argument is that large impacts may be much more frequent in other planetary systems, and that one is worth discussing. And that sort of relates to the things that Jonathan talked about with the giant planets and how the solar system forms. And then finally, there's this one about chaotic obliquities and the influence of the moon. So let's think about nitrogen, N2. First of all, why is it important? Well, the most important reason is that biology needs fixed nitrogen to make amino acids or to make nucleic acids that go into DNA and RNA. And so, of course, you need nitrogen. That, by the way, is a problem for Mars today. If you wanted to make Mars habitable, there's not much N2 in the atmosphere. There may be nitrates in the soil, but nitrogen would be one of your biggest problems with terraforming Mars. There are some other reasons why nitrogen is important, and one of them is illustrated right here. I don't know how many of the young people in here remember Apollo 1, but the first of the Apollo space capsules the crew never made it into space, and because they were testing the Apollo capsule on the launch pad in Houston, and there was a cockpit fire which killed all 3 astronauts. well, why did this happen? It happened very quickly, and they were, before they could get the astronauts out. It's because NASA was running pure oxygen atmospheres inside the capsule. At the time, it was considered, that way you could keep the partial pressure of air in there. You only had to have 20%, the same partial pressure of oxygen that you have today. So about 0.2 bars of oxygen. And I guess, I don't really understand the logic fully, but if NASA was thinking if you have a spacecraft up there in space, it's easier to build it if you have a lower pressure inside the space capsule.
But it's also weight. You don't have to carry the nitrogen to pressurize the capsule. The additional nitrogen to pressurize it up to 1 bar.
Oh, that weight has to be a trivial amount, I would think.
I don't think so.
Oh, okay.
It is.
Well, at any rate, so there, NASA was trying to do the right thing and keep the weight down and whatnot, but fires burn just uncontrollably in pure oxygen. And there's some simple physics behind it. Of course, the oxygen is fueling combustion by combining with whatever it's burning with. But the air that comes into a flame also cools it by convection. So it's carrying heat away from the flame. And when you have a non-combustible gas like N2 in there, then that increases the amount of heat that's carried away by convection without bringing additional oxygen to fuel the fire. If you go to pure oxygen, then every time you bring in air, you're bringing in more combustible material. And so, the frequency, well, the intensity of fires is just a very nonlinear function of the oxygen mixing ratio in the air. Which, after that fire, NASA very quickly figured that out, and ever since then they've used air mixtures in spacecraft. Then there's a slightly less obvious reason why nitrogen is important on Earth. It stabilizes the Earth's atmosphere against water loss. And this actually goes back again to my talk on the runaway greenhouse. I showed you this slide here. This is from increasing the CO2 partial pressure on the Earth. A point that I don't know if I made really well is that you start to lose water when the stratosphere becomes wet. And the stratosphere becomes wet, you can tell when that's going to happen because it's directly related to the mixing ratio of water vapor, or the concentration of water vapor near the surface of the planet. When that concentration near the surface, which is this solid curve, gets greater than about 20% by volume or about 10% by mass, then that's when the stratosphere becomes wet. The tropopause cold trap gets wiped out. And again, this was shown by Andy Ingersoll back in a paper in 1969. So think about what would happen to the Earth's atmosphere today if you took out the nitrogen. And let's just assume that the surface temperature is the same as today, because you wouldn't lose that much warming because nitrogen's not a greenhouse gas. But then you would just have the same amount of water vapor and the atmosphere would be 5 times thinner. So the mixing ratio of water vapor near the surface would be 5 times higher. And in fact, the easiest thing to do is, suppose you just had an atmosphere that was pure water vapor, then that would be pure water vapor all the way up. And so a pure water vapor atmosphere would not be stable. It would just be lost to space because there's no diffusion limit essentially to stop it. And so you actually need water vapor then to help stabilize the ocean. All right, well, where does the nitrogen come from? I think Jonathan talked about this at least a little bit in his lectures. We think that most of it comes in as a component of organic matter. It certainly doesn't come in as N2 in meteorites, and there's not much nitrogen in most minerals, so this nitrogen is bound to organic matter. And at least the place where I think it comes from is from carbonaceous chondritic type material that originates in the asteroid belt. Now, Jonathan, you talked about this, and apparently there's some debate as to how much carbonaceous chondritic material you can include in the Earth. So my impression is that if a planet gets carbon and gets water, it's also going to get nitrogen from these same sources.
Actually, a quick calculation we could do in the coffee break is assume that 1% of the Earth is carbonaceous chondrite, and then let's see if there's enough nitrogen. I think the answer is yes, there's more than enough.
Right.
I haven't actually done it.
Yeah. So anyway, there probably there probably is a source of nitrogen if you have some component of carbonaceous chondritic material. The other argument about nitrogen this is the one that comes from Jim Lovelock and the Gaia hypothesis. He argues in that book that if you didn't have biology, didn't have life, all of Earth's N2 would get converted to nitrate in the oceans, and then you'd have no nitrogen left in the atmosphere. And the argument is fairly simple. Today, one of the ways of fixing nitrogen, bugs fix most of the nitrogen. John's talked a lot about nitrogen fixation. But you can also fix nitrogen, that is, break the N2 bond by lightning. And so in today's atmosphere, when you get a lightning storm like this, N2 and O2 combine to give NO, and that NO gets oxidized in the atmosphere to nitrate, which then is soluble and goes into the ocean. And there's lots of estimates. We think we know how fast that's occurring. This would happen even if you didn't have free O2 in the atmosphere, because you'd still get shock heat. If you just had CO2 in the atmosphere, you heat up N2 and CO2 in a lightning bolt and you'll still produce NO, and the ultimate result is you still end up making nitrate or nitrite, and that would go into the ocean. Now, Lovelock then points out that today the way that nitrate gets recycled back into N2 is by bacterial denitrification, which we've talked about just a little in here. Organisms, the denitrifying bacteria, take nitrate and they oxidize that to nitrite, and then through various pathways they either go back directly to N2 or to nitrous oxide, N2O. And the N2O then goes into the atmosphere and that gets photolyzed and goes back to N2. So the nitrogen cycle is biologically mediated.
I make a comment. I mean, a lot of my colleagues who deal with early life love the concept of an early nitrate ocean as stimulating life. And so there's a number of models that say if you can actually make nitrate in this method from N2, then that's going to actually be a really excellent source of oxidant for early life.
Well, I think you definitely can make nitrate in the model. We make nitrate in our models, and so that part of it works. But it doesn't necessarily mean that all the nitrogen is going to end up in the ocean as nitrate. And the reason has to do with something else that you've talked about, John. It's this hydrothermal circulation. There's a lot of it going on the seafloor today, and probably there was more back in the past. But when these mid-ocean ridge hot smoker, black smoker environments are very reducing. And so all of the entire ocean today passes through the really hot axial parts of the hydrothermal vent systems about every 10 million years.
No, it's now under 1 million.
Under 1 million, so the circulation has speeded up. Those are
even today, and probably tens of thousands in the RTM.
Okay, so you're cycling that water through this reducing environment, and when that happens, the nitrate would get reduced down to either N2 or ammonia.
Can I make a comment on this? Because there's 3 papers out on this, including 2 that with the same kind of minerals that are found in the vents were able to actually convert N2 to nitrite and nitrate. So it's not just reducing nitrate, you can actually reduce, not to nitrate, but reduce nitrogen to ammonia. And that's been demonstrated in the laboratory under hydrothermal vent conditions.
All right, so that
just circulating even N2, which is super saturated in the deep sea, can be converted by minerals to ammonia.
Yeah. So that's actually good for the origin of life, and because that ammonia is what organisms really need. From the standpoint of the stability of N2, it amounts to the same thing, because if you take ammonia and put that into the atmosphere, then I went through that ammonia photolyzes in the atmosphere. It goes back to N2 and H2. So either way, if you create N2 or if you create ammonia in the mid-ocean ridge vents, you're going to end up recycling nitrogen back into N2. And so N2 is stable in the Earth's atmosphere even in the absence of life. We made that argument in our 93 paper on habitable zones, and I think that's still correct. Okay, what about Jupiter? You know, there was a paper, and Jupiter affects the frequency of large impact events on the Earth. Large impact events can have a serious impact on life. We all know about the KT impact, this big 10-kilometer diameter object that hit the Earth 65 million years ago and wiped out the dinosaurs along with many other forms of life. There was a paper that was written by George Wetherill back in 1994. I don't think we've mentioned George's name in this conference, but Wetherill was really one of the pioneers of these models of planetary accretion. And he was working back in the time when computers were much slower than today, so he didn't do the types of fancy n-body codes that Jonathan talked about. He did some rather simple calculations based on this old thing for tracing how meteorites get to the Earth. It was very clever, actually. Wetherill was a good mathematician. But George he got interested in astrobiology, and he wrote this paper pointing out that when you have long period comets coming in from the Oort cloud, most of them never get on orbits that would hit the Earth, because long before they do, they suffer a close pass by Jupiter. Jupiter has the most effect because it's the biggest planet in the solar system. And they get kicked into, they get ejected from the solar system, or they're basically deflected so that they don't get to the inner solar system. So Jupiter is a shield against Oort cloud comets. And I think that part of the argument is correct. But on the other hand, and then there's numbers in Wetherill's paper. So if you said all the impacts on Earth are from these long period comets, today we get big impact events on the Earth about every 100 million years is the estimate. And if they were all coming from the Oort cloud, Wetherill says they would be 10 to the 4th times more impacts without Jupiter. So instead of getting a large KT-sized impact every 100 million years, you would get one every 10,000 years. And if that was right, that would be serious business, because it would be hard to get complex life going if you had a major extinction event every 10,000 years. But the argument's complicated. In fact, Jonathan's probably more the expert on this than I am. This question of where the big impacts come from and how frequent they would be if you don't have a Jupiter is actually really complicated, because you've got you've got the Oort cloud out here, which is this spherical shell of comets. There's also the Kuiper belt, which are the comets that exist in the plane of the solar system. They're left over from accretion. Jupiter was involved in the formation of the Oort cloud. Jonathan talked a little bit about this, that those comets in the Oort cloud, we were certain had to form in the disk of the solar nebula, and then they got scattered out into that cloud by interactions with the outer planets. There's also an asteroid belt, and a lot of the impactors, the KT impactor probably came from the asteroid belt. You can make pretty good arguments that that was an asteroid and not a comet, based on the iridium abundance. And why do we have an asteroid belt? Well, that's because we have a Jupiter. Probably if we didn't have Jupiter, we'd have a planet there where the asteroid belt is. But now that we've got the asteroid belt, what is it that makes the asteroids, knocks them out of the belt and puts them into Earth-crossing orbits? That's resonances with Jupiter. So what actually happens is these asteroids are going around in nice stable orbits, and then occasionally they collide with each other and they get kicked into one of those resonances. What are the gaps? There's Kirkwood gaps. Yep. So there's the 3-to-2 resonance, I think, is the most unstable one. And so if an asteroid gets into that 3-to-2 resonance, then you can show mathematically that its eccentricity gets pumped up and it can get pushed into an Earth-crossing orbit. So Jupiter is not only shielding us from Oort cloud comets, it's perturbing the asteroid belt and causing collisions with asteroids. And I think the bottom line is that the influence of the outer planets on is very complicated. I'm sure they do influence the bombardment of a terrestrial planet, but I don't think you can just pick a number like 10 to the 4th and say that would be the frequency of large impacts in the absence of Jupiter. It's actually very complicated, and it'll depend on the entire structure of the planetary system.
Yeah, and that's right.
Right.
You said it right.
Yeah. So
I like this last point, though. You want to have some impacts to keep things moving along.
that's right. Without impacts, many paleontologists have made this argument: evolution can get stuck. Arguably, it got stuck in the dinosaur phase. The dinosaurs ruled the Earth for 150 million years, and mammals were there. Mammals originated about the same time as dinosaurs did, but they didn't get any bigger than shrews, because if you got bigger than a shrew, you got eaten by a dinosaur. And then once the dinosaurs got wiped out, these little shrews started growing, and that's when, that led to the evolution of us. So you do need a certain frequency of impacts, or you probably won't get to intelligent life. And there's been questions as to whether the dinosaurs would have developed intelligence. Velociraptor was actually pretty intelligent, but on the other hand, he was also very well armed, and it's not clear that he needed to develop a big brain and tools. Okay, so this brings me to my last argument for this morning. This is the most fun one, actually. This is the effect of the moon. How am I doing on time? Okay. This is the effect of the moon on the Earth's obliquity. And it's quoted in Rare Earth, but the argument really comes from Jacques Lescar and colleagues. Lescar is this really brilliant mathematician in France, at University of Paris, I think it is, and he's one of the two, I think. Well, there's several really brilliant mathematicians in this game, but Lescar and Jack Wisdom at MIT did a lot of the pioneering work. Lescar has shown that he had a couple of papers in 1993 that were really seminal papers, and in those he showed that the Earth's obliquity would be chaotic if the Earth did not have a moon. He also showed that, and this was not new to him, other people had shown previously that Mars' obliquity does vary chaotically on timescales of tens of millions of years. Lescar showed that the Earth would do the same thing. In fact, the Earth would be worse than Mars. It would fluctuate from 0 to 85 degrees on a time scale of tens of millions of years. Now, this is the key figure from his paper, and I've plotted the Earth, the present Earth, and the Earth with no moon on this. It's kind of a complicated diagram. This is the planet's obliquity in degrees here, and this is the precession constant on the vertical axis. That's essentially the rate at which the spin axis is going around like this. Although I think you have to multiply it by the cosine of the obliquity to get the actual spin rate. What Lescar did, he does sort of semi-analytical calculations. I said he's a good mathematician. He does series expansions of Laplace's equations. Laplace, the French have this whole history of doing astronomical calculations, and it goes back to at least Laplace. Laplace wrote down a set of equations that govern the motion of the planets. And back then, of course, you couldn't solve anything numerically, so you had to do expansions. So Laplace did some series expansions, which I've never looked at. Lescar followed up on that, but he used Mathematica, and he carries out his series expansions to 150,000 terms. So he does use the computer to do that. But then he drops the 100,000 terms that don't matter so much, and he just keeps 50,000 terms in the series expansion. And then he integrates the equations of motion, but he can do it very fast, much faster than anybody else can. Everybody else uses these symplectic integrators that Jonathan mentioned, which are numerical. They're also very clever, but they're slower than what Lescar does. And so Lescar, in this case, he's integrating the solar system and also calculating the Earth's obliquity. He did a series of 18 million year integrations for the Earth, where he starts the planet at different precession constants and different obliquities and integrates for 18 million years. And what happens is the obliquity changes with time. And that's this fuzzy region in the diagram here. Now, also on the diagram, on the right-hand scale here, that's the spin rate of the Earth. It's the relationship between the Earth's spin rate and the precession constant if the moon was not present. And so why is this? It's kind of subtle. When the Earth is spinning, it kicks out an equatorial bulge. And what's causing, there's a torque that's exerted by the sun on that equatorial bulge. And in fact, the moon also torques the equatorial bulge. So that's what's causing the Earth to precess. Now, if you don't have the moon there, then the precession constant is just directly related to the spin rate, because the spin rate decides the size of the equatorial bulge. You really have to read Lascar's papers to understand how this works. But anyway, if this is the chaotic region in here, this fuzzy region where Lascar's calculations wander, the present Earth is up here. So that's in a stable region. The Earth's obliquity is 23.5 degrees, and it fluctuates by about plus or minus one degree on a 41,000 year period. That's one of the Milankovitch cycles that drives the ice ages. If you just take the moon away, doing nothing else, then the Earth's precession rate would be slower, because that moon is torquing on the equatorial bulge. It's spinning up the precession. If you take away that, then you just have the sun torquing on the equatorial bulge. So the precession rate is slower, and if the obliquity is the same, it puts the Earth right down here. Now, you can't really tell what this area is in here. That's actually chaotic too. It's just Lascar's calculations. He didn't do his calculations long enough to populate that region. So the Earth is in a chaotic, would be in a chaotic region where the obliquity could vary from 60 up to 85 degrees. And of course, if it's at 85 degrees, then the pole is, at solstice is nearly pointing at the sun. It's just like Uranus in our present solar system, which has an obliquity of, 98 degrees or 91 degrees. It's just pole on basically some of the time. So that's the argument then, and Ward and Brownlee quote this, and they say, okay, if you didn't have a moon, then the Earth's obliquity would be chaotic. And then, of course, there's this logic here. We talked about the giant impact event that forms the moon. Jonathan mentioned that moon-forming impacts are rare, not because large impacts are rare, but because they have to happen at the right impact angle and velocity, and you need a big object to do that, size of Mars or maybe even a little bit bigger. Just as an aside, I saw this painting up on the trail on the mountain above here. Did anybody see that? It's there's this whole history of the solar system on that hike up to Brete. And this is a painting by William Hartmann that is, I saw that sign at this station just above Villar. So it's a very popular painting of this. Anyway, so if moon-forming impacts are rare, according to the Ward and Brownlee, then planets with stable obliquities would be rare. But now let's think about that a little bit more. First, you have to consider what is it that causes the chaos in this system. And this is another figure from Lascar's paper here. The chaos is caused by when the precession rate of the spin axis matches up, is in resonance with the secular motions of the other planets. And the secular motions that I'm talking about here are the precession of perihelion of the planets, and also the precession of their line of nodes, the place where all these planets' orbits are inclined to the invariant plane of the solar system. If you just take all the angular momentum vectors of the planets, that defines the invariant plane. And planetary orbits sort of roll around like a dinner plate on a table, like this. So the line of nodes precesses around. And when the spin axis precession rate matches either of those precession rates, that's when you get the chaos. So here from Lascar, this is the frequency of these secular motions, and he's got them labeled. If I remembered right, these are labeled by which planet is causing the secular perturbation there. The two that are most important for Earth are Jupiter, because it's very massive, and Venus, because it's close. So those have the most effect on the Earth's obliquity. The Earth today is sitting right out here. Its precession rate is about 55 arc seconds a year, so it's just outside this thicket of secular resonances with the other planets. And if you take the moon away, then the precession frequency drops to 18 15 arc seconds per year, puts it right in the middle of that big packet of resonances there, and that's what causes the obliquity to vary chaotically. All right, so now let's think what would happen more generally. You know, if you think about what the moon has done to the Earth's spin rate. First of all, back to this diagram, notice that the Earth is right here. It would have a 24-hour spin period if you just took the moon away. If the Earth is rotating faster than about 12 hours, though, then at a 23.5 degree obliquity, you get up into the stable region. So if the Earth had a 12-hour period, it would be stable. And if you then think about what the moon has been doing to the Earth's orbit, the Earth's spin, the moon has been slowing down the Earth's spin with time because of tidal drag. So that we know that the Earth was spinning faster back in the past. There's actually data back to the beginning of the Cambrian from corals that have these daily rhythms recorded in them. So we think it was a 20-hour spin rate 600 million years ago or so. We think that initially the Earth was rotating at about a 4 or 5 hour rate. It was rotating very fast, and so that would be in the stable region. But why was it rotating fast? That was because of the moon forming impact. And so you get this whole, you're sort of chasing your tail on the arguments here. The fact is, I think we have no way of predicting from accretion models how fast a planet would spin if it didn't have a moon. And also, because you have to know what those secular frequencies are from the other planets, it depends on the orbits of all the other planets in the system. And so again, it's one of these arguments. There may be planets out there like the Earth that do have chaotic obliquities, but you can't just say, you know, planets with large moons are destined to be chaotic, because it's not necessarily true. And then finally, one more slide. What if the planet's orbit is chaotic? That's a possibility. Well, that's something you can study with the climate model. And I had a PhD student, Darren Williams, who did that as part of his PhD thesis several years ago. He took one of these energy balance climate models that I described for snowball Earth calculations and just ran planets at various obliquities. So here he's calculating. What he did is he took the present Earth and then he did it with different amounts of CO2. Because if you have more CO2, suppose the planet is farther out in the habitable zone, it'll develop a denser CO2 atmosphere, and that tends to buffer the surface temperature because it acts as a big heat capacitor. You've also got an ocean, and the ocean acts as a big heat capacitor. So actually marine life doesn't care if the planet is at high obliquity because the ocean temperature doesn't change that much. The surface temperature does fluctuate. If you're up at, say, 85 degrees, you're up near one of the poles, you get a really big seasonal cycle in temperature. But if you're near the equator at 5 degrees north here or 5 degrees south, I don't know if that's on there, then the temperature fluctuations are still not that bad. They're sort of comparable to what they are on present Earth. So that's really it. Let me leave you some conclusions here, which are not really conclusions, but points for discussion. You know, Ward and Brownlee, I think, make some very good points in their book that evolving complex life is difficult, but I'm not as pessimistic about it as they are. Planets themselves, I think, are very common, and I think we're finding that both from the radial velocity measurements and from Kepler. Habitable planets may be reasonably common. That's still a speculation, but Kepler is starting to provide some data on that, planets in the habitable zone. We don't know about the origin of life, and I'm not going to take questions about that, but John may. The evolution of oxygenic photosynthesis, that strikes me as one of the most difficult steps, but it may or may not be difficult. And then finally, we are interested in the evolution of intelligent beings, and the best way to find out about that is to use radio telescopes and continue doing SETI, and maybe we'll figure that out at some point. Thank you. John.
How habitable would the Earth be if it never had a moon? I mean, we talked about being in this chaos region, but what conditions would exist that could prevent life from actually...
That was his last slide.
Yeah, well, so if it was rotating faster than 12 hours, it would not be chaotic. But we can't, I don't think, predict how fast the Earth would rotate. Somebody mentioned to me, we were talking about this over dinner last night or the night before, and they mentioned tidal cycles and the origin of life. So one theory of the origin of life, which is not the one that you discussed, John, but the warm little pond theory, requires that you have tidal cycles, tides going in and out, and so you get wet, dry cycles, and that leads to life. You wouldn't get those big you would still get tidal cycles because you still have the sun, so they'd just be smaller than they would be.
Yeah, actually, the sun's tidal effect is about the same as the moon.
It's about half that of the moon, right?
So, you know, I mean, it's hard for me to imagine that a factor of 2 is going to make a difference in tidal amplitude.
Yeah, although the moon's tidal cycles were originally a lot higher because the moon was closer to the Earth.
You're right.
Right, so you had some really big tidal cycles. So if tidal cycles are important in the origin of life, maybe that's a rare Earth.
How much land mass would have there been in that period?
Probably very little, I think. Yeah, so it's better. There's more environment under the ocean. Yes?
There's something I didn't understand in the Alaska plot. Is why the present Earth has a 7-hour Earth?
Oops, let me put the scar back up. There we go. Yeah. So the question is, present Earth is up there. The scale on the right is the day length if you don't have the moon there. So with the moon there, that scale on the right does not apply. And so what's really being done here, LaScar is doing calculations in terms of the precession constant. And the Earth's precession constant is 55 arc seconds a year. So the Earth is up here. Of course, doesn't have a 7-hour day, but that's how fast the Earth would have to be rotating to have a precession constant of 55 arc seconds a year without the moon being present. Jonathan?
Yeah, 2 points. First of all, there is actually plenty of nitrogen in carbonaceous chondrites, at least, even in the carbonaceous chondrites. So if you accept 1%, which some geochemists do and others don't, there's plenty. Even less would give it to you. The second point is with respect to this magnetic field business. Remind me why Ward and Brownlee argue that fields are rare. I mean, we find permanent magnetic fields in unexpected places, like Ganymede, for example, has a permanent dipolar magnetic field. So that seems to me, surely, as you've said, a very weak argument. You cannot argue that the Earth is rare by dint of having a magnetic field. That doesn't make sense.
I would have to actually, it's been a while since I've reread that section. The part that I remember is the tidally locked planets will rotate more slowly.
That they will, yes.
So that might be a point. Yes?
Is there any research on the necessity of the Milankovitch cycle on the evolution of life? Because how they drive biodiversity and evolutionary pressure.
Yeah. So that's a good question. These Milankovitch cycles drive the ice ages, and some people have argued that the ice ages is what caused civilization to come out, and maybe intelligent beings. It's in some ways people were more intelligent, and that allowed them to survive these glacial interglacial cycles better. There's a new paper out by a guy named David Waltham. This is in Astrobiology journal, and it's a new rare Earth argument. He's arguing that Milankovitch cycles on the Earth are abnormally slow, and that in other solar systems the Milankovitch cycles would be faster. He's done a bunch of N-body simulations and done sort of many different types of planetary arrangements, and then he calculates the Earth's obliquity fluctuation, and he finds it's sort of a Bayesian analysis type thing. He finds that the present cycles are slow, and then he argues that that's important for the evolution of intelligent life. But
there's a fundamental philosophical problem here, which we should talk about during our the final session that we have. This whole Goldilocks thing, that if something is different from what we have here, it must be bad.
Yeah, it's the anthropic principle, right, is what that's called. Yes, Terry.
I have one question, one remark. The question is that if you change the obliquity, you're also going to change all the plate tectonics, I guess.
I don't think so.
Well, if you rotate differently, then the plates, which are certainly driven in part by the rotation of the Earth, will change.
Well, the Earth assumes a shape that includes the tidal bulge, but then the plate motions are driven by mantle convection beneath that. And so I'm not sure that that would fundamentally change plate tectonics, although I'm not a geophysicist, so...
If when you look at these arguments from a bit further, you have the impression that people are trying to do statistics, or large bodies of statistics, out of Venus, Earth, and Mars, and trying to deduce out of these three special cases something which would be true for an ensemble. And that does sound not a particularly strong intellectual...
I think that's a very good point. You know, we don't have enough planets in our own solar system to really generalize, and that's why these studies of exoplanets are going to be so useful. Yeah, back.
Actually, the question is linked to that. When you look at the Kepler results, you see a lot of close-in, rocky or small planets. Would it leave room for other planets to exist in habitable zone?
Yes.
Oh, Jonathan's nodding. I think, yes, the planets that have been found so far close in by Kepler don't preclude planets farther out.
Yeah, even giant planets. Sean Raymond did a study in which he showed that a really close-in giant planet is not going to affect the stability of an Earth at 1 AU.
Yeah. Although it does affect how the planet would evolve, because that giant planet migrates through the habitable zone, and then
But it migrates very early.
very early.
And Doug Lynn showed that you can then restore the particle disk. So.
Yeah.